In today's example, we will learn how to calculate equivalent circuit for networks with dependent sources. Let's look at a circuit diagram as shown below. In this circuit diagram, we have one independent source, which is Vs, and one dependent source, which is GVC, whose current is controlled by another voltage inside this circuit. We call it Vc. And then, for the first step, we would like to calculate what is output voltage, Vo. So in order to calculate Vo, we need to analyze this circuit. So today, we would like to utilize node analysis. For node analysis, first of all, let's choose a ground. It makes good sense to utilize the bottom line as a ground. The reason is it connects most number of devices. After we choose this as ground, then it's easy to decide that the node labeled as plus will have potential of Vs because it's directly connected to ground across the source. And then another node that we will focus on will be this one. Let's call its potential as E. We can analyze node E, for example, using KCL. According to KCL, there is an electric current going into this node this way, and we find that this current is nothing but GVC, because this is the only path that the current can flow after they go outside this current source. And then there is this current. So we know this current can be calculated as 0, which is ground, minus E divided by R1, which describes current that goes through R1. Of course, there will also be current going from right and toward this direction, because in this case, it's open circuit for VO. So actually, there is no current going to the node from this direction. So now we get GVC plus 0 minus E divided by R1 is equal to 0. Then, using this equation, we can express the electric potential E as GR1 times Vc. However, Vc is not explicitly given in this problem. We still need to further decide what Vc is using the known value, which is Vs, R1, and R2, as well as G. In order to decide on Vc, what we can do is we will look at the two terminal potential, plus and minus terminals. For the plus one, we already decide its electric potential is Vs. Now what about minus? Previously, we learned that minus sign, this minus terminal is connected to this whole line. So its electric potential is also E. So now we have this relationship. Vs minus E is equal to Vc. Now let's substitute the expression for E into the bottom expression. So basically, we have Vs minus GR1 Vc equals Vc. This is by substituting expression of E. Then from this equation, we can build up a relationship between this control voltage Vc and then the input voltage Vs. So it's easy to see Vc can be expressed as Vs divided by 1 plus GR1. So not done yet. We still need to determine what the output voltage is, VO. Now we know what VC is. It's very easy to go from VC to VO because we can easily observe that VO is nothing but this potential that we defined, E. So we have VO is equal to E, and then earlier we decided E is equal to GR1 times VC. That is GR1 times VC. And we also have the expression for VC, so that will be GR1 divided by 1 plus GR1 times VS. Sorry, this is, yes, we replace the expression of VC into this expression. So we get GR1 divided by 1 plus GR1 VS. So this is the output voltage for this circuit, which contains the dependent source. For the second part of this example, let's calculate the equivalent circuit. Particularly, we would like to calculate the Thevenin equivalent circuit for this network. So in the end, we would like to build up an equivalent circuit like this, which contains only one independent source and one resistor in series. So this is VTH and this is RTH. We would like to decide on the value of VTH and RTH. So first of all, for VTH, according to the definition, it's the open circuit voltage of the original network. Actually, this is nothing but the VO that we just calculated, because when we calculate VO, we didn't put any load there, so that's open circuit voltage. So VTH is equal to VO, which is what we just calculated, GR1 divided by 1 plus GR1 times VS. The next question is, how do we calculate RTH? For the calculation of RTH, we remember the rule is we have to remove the independent source, but keep the dependent source. So now let's draw the circuit after this independent source is removed. So we remove this independent source, Vs. It's important to know that this independent source cannot be simply removed. The reason is its value is controlled by VC, but the VC is not necessarily zero, particularly when you put a test source, when you put some external circuit onto this output terminal. So it has to be kept here. Now the question is, what is the resistance that one will see if you look into the output port? This is not a trivial problem for this part. So we cannot immediately say what is the Thevenin resistance. So the way to solve it is to put a test source as an output terminal. So here we put a test voltage source and we call its value is VT. And we see the current that as an output port is IT, the test current. Now we need to decide the relationship between IT and VT, because their ratio will give us this equivalent resistance, RTH. So now let's see how we can decide on the relationship between VT and IT. Again, we can utilize node analysis. We choose this as ground. Again, very quickly, we can decide on the node voltage of this plus terminal, which is 0, because it's directly connected to ground. And then another node that we will focus on is this E. For node E, we will see that its voltage is also this test voltage source, voltage, VT. Using KCL, we see there are 3 currents that we need to consider. One is this, which is GVC, and the other is this, which is the test current source, which you would like to calculate, as well as the current that goes through is R1, which is given by minus E divided by R1. So we get this should be equal to 0. Since we know E is equal to VT, so we can directly replace E with VT. So let's do it. This is directly represented as VT. So this question almost gives us the relationship between IT and VT, except there is one unknown, which is VC. VC is not explicitly represented. So we need to calculate what VC is using IT or VT. So now let's focus on this pair of terminal. We already decided this terminal is 0. Now the question is, what is the voltage for the minus terminal? We see the minus terminal is directly connected to the node of E, which is the same as VT. So VC negative terminal has the potential of VT. So now we can easily calculate VC is equal to 0 minus VT, that is minus VT. So by replacing the expression of VC into this KCL equation, what we will get is minus G VT plus IT minus VT over R1 is equal to 0. So this will further give us the relationship between VT and IT. This is equal to 1 over G plus 1 over R1. You can further simplify it, which is 1 plus G R1 on bottom and R1 on top. So this is the relationship between the test voltage and also the test current. By definition, this is the Thevenin resistance. Okay, so far we have decided both the Thevenin voltage as well as the Thevenin resistance. So we see that such a complicated circuit which contains dependent sources can be converted into a simple circuit with only one source and one resistor, utilizing Thevenin theorem. Before we end this example, let's focus a little bit more on the value of the Thevenin voltage and Thevenin resistance. If we look at Thevenin voltage, it's GR1 divided by 1 plus GR1 times Vs. It's easy to see this is smaller than Vs. So this means if your input is Vs, the output is even smaller than the input. So this means the voltage gain is smaller than 1. So it does not amplify the voltage. But still, we utilize this as a useful amplifier circuit. The reason is because if you look at the Thevenin resistance, you will see that it's equal to R1 divided by 1 plus GR1. So in most cases, if G much larger than 1 over R1, which is usually guaranteed in real circuit, actually this will give you 1 over G. Usually, this 1 over G can be very, very small because this conductance G is usually made to be very large. So that means this RTH is very small. That's equivalent to say that this serial resistor is very small, which makes this circuit more or less more like an ideal voltage source. Because for ideal voltage source, you want the serial resistor, internal serial resistor, to be as close to 0 as possible. So that's the advantage of this circuit. Basically, it minimizes the output resistance. So this circuit is a very useful circuit as a voltage buffer.